Hello and welcome to Late Night Space. Before we begin, please take a moment to like the video and subscribe to the channel. It genuinely helps this quiet corner of the cosmos continue to grow. And if you'd like, leave a comment telling everyone where you're listening from. It's always fascinating to see how many different points on Earth are tuned in, while we talk about what lies far beyond it. Tonight, attention turns to something unusual. Astronomy is a science of prediction. Stars form in predictable ways. Galaxies grow through understood processes. Gravity shapes structure with remarkable consistency. Modern cosmology, guided by general relativity and refined through decades of observation, allows scientists to simulate the universe with extraordinary accuracy. And yet, scattered through that vast structure are objects that seem to resist expectation. Galaxies as large as the Milky Way, but so faint they are barely visible. Stars moving so fast they are escaping their own galaxy. Neutron stars with magnetic fields so extreme they stretch the limits of known physics. Black holes that may have formed before the first stars ever existed. These objects are not violations of physical law. They are not science fiction, but they are uncomfortable. They sit at the edge of probability. They force astronomers to recheck measurements, refine simulations, and revisit assumptions. Not because the laws of physics have failed, but because the universe is vast enough that even rare outcomes eventually appear across hundreds of billions of galaxies, each containing hundreds of billions of stars. Unlikely things are not only possible, they are inevitable. Still, when one of these objects is discovered, there is always a moment of pause, a quiet recalibration, a reminder that prediction and reality do not always align neatly. Tonight, the journey moves gently through these anomalies, through the faint giants, the runaway stars, the extreme remnants, the ancient black hole candidates. Each one real, each one measured, each one pushing against the comfortable boundaries of theory. The universe, it seems, does not break its rules, but it does explore their edges. Out there, beyond the atmosphere, nature repeats itself with an almost stubborn consistency. Gravity pulls the same way in every quiet corner of space. Gas clouds collapse when they become heavy enough. Stars ignite when their cores become hot and dense enough. Galaxies assemble into spirals and ellipses and faint smudges, following patterns that can be studied, compared, and, to a surprising degree, predicted. That predictive side of astronomy is one of its strangest achievements. A human mind can look at a sky full of scattered lights and say, with real confidence, what should happen next? A large part of this confidence comes from general relativity, Albert Einstein's theory of gravity. Instead of treating gravity as an invisible pulling force across empty space, general relativity describes gravity as the curvature of space-time itself. Mass and energy shape space-time, and everything else moves along those curves. The idea sounds philosophical, but it is practical. It predicts measurable effects. Starlight bends as it passes massive objects. Time ticks differently in stronger gravitational fields. Even ripples in space-time, called gravitational waves, were predicted long before they were detected. That detection came from the Laser Interferometer Gravitational Wave Observatory, usually called LIGO. When LIGO measured gravitational waves from merging black holes, it was not simply a dramatic moment for astronomy. It was another confirmation that the predictive framework is real. The universe behaves again and again in ways that match what the equations said it would do. Stars also follow rules that are, in many ways, wonderfully repetitive. Stellar evolution theory describes how stars form from cold clouds of hydrogen and helium, how gravity squeezes those clouds until the core becomes hot enough for nuclear fusion, and how a long period of stability follows. That stability comes from a balance. Gravity pulls inward, trying to compress the star. Pressure from hot gas and radiation pushes outward. When the two are in balance, a star can shine steadily for billions of years. Inside a star, hydrogen nuclei fuse into helium. A small amount of mass is converted into energy. The relationship is captured by Einstein's famous statement that energy equals mass times the speed of light squared. In plain terms, a tiny loss of mass produces a huge release of energy, and that energy is what keeps a star bright, warm, and stubbornly alive. Once those principles are understood, larger structures begin to look less mysterious too. Galaxies are not thrown together at random. They form within gravitational wells. They merge, grow, and reshape. Their stars form in bursts or in slow, steady rhythms, depending on their gas supply and environment. Over cosmic time, galaxies gather into clusters and superclusters, and between them stretch enormous regions of emptiness, called voids. To describe that large-scale story, cosmologists often use the Lambda Cold Dark Matter model. It is the standard cosmological model used to explain how the universe expands and how structure forms. In this picture, dark matter provides much of the gravitational scaffolding that helps galaxies form. Dark energy, represented by the lambda term, accounts for the accelerated expansion of the universe. Ordinary matter, the kind that makes stars and planets, is only a small part of the total cosmic budget. This is where astronomy becomes quietly audacious. It is one thing to describe a single star. It is another to describe a universe full of them, spread across immense distances, evolving over billions of years, and still claim that the broad outline should be predictable. And yet, it often is. Large sky surveys such as the Sloan Digital Sky Survey have mapped millions of galaxies and measured their positions and properties. These maps are compared with huge computer simulations. The Millennium simulation is one famous example, and the Illustris project is another, both aiming to recreate the growth of cosmic structure from early conditions to the modern universe. In these simulations, gravity is allowed to do its work over billions of years, and galaxies emerge in patterns that can be compared with real observations. When those patterns match, it feels almost unreal. Nature is being caught behaving as expected. Organizations like NASA and the European Space Agency collect mountains of data from space telescopes and missions, while ground-based observatories add their own measurements from the surface of Earth. Astronomers do not simply look up and admire. They measure, they count, they chart, they compare. They build models that say, in effect, given these laws and these starting conditions, this is what should exist. But there is a crucial detail hidden in the word should. In astronomy, should exist usually means should exist often enough to be unsurprising. It is not a statement of certainty, it is a statement of probability. The universe is unimaginably large. When the sample size is that enormous, rare outcomes stop being rare in the everyday sense. Even improbable things can appear simply because there are so many chances for them to happen. Still, astronomers notice when something lands far out on the edges of expectation. Not because it breaks physics, but because it makes the comfortable predictions feel a little less comfortable. One of the most unsettling examples is strangely gentle. It is not a violent explosion or a brilliant burst of radiation. It is something faint, almost shy. Ultra-diffuse galaxies. These are galaxies that can be enormous in size, sometimes comparable to the Milky Way, yet they contain far fewer stars than a galaxy that large is expected to have. Their stars are spread thinly across a wide area. Instead of a bright, dense glow, they present as ghostly smudges, barely above the background darkness of space. Some are so faint that they were effectively invisible to earlier surveys, not because they were far away, but because they were spread out and dim. The discovery and careful study of these objects was pushed forward by researchers including Peter van Dokkum, and by instruments designed to see what most telescopes miss. The Dragonfly telephoto array is a particularly important example. It was built to detect extremely low surface brightness structures, the kind that get lost when scattered light, and optical imperfections swamp faint signals. Dragonfly helped reveal galaxies that looked almost like someone had tried to draw a normal galaxy, then erased most of it, leaving only the lightest trace behind. Here is the uncomfortable part. In the Lambda Cold Dark Matter model, galaxies form within dark matter halos. A massive halo is expected to hold onto gas effectively, encouraging star formation. A large galaxy by size suggests a significant gravitational structure. It suggests mass. It suggests a history of growth and retention. So what does it mean to find a galaxy that is physically large, but made of remarkably little starlight? In some cases, ultra-diffuse galaxies appear to contain unusually high amounts of dark matter for the number of stars they have, almost like dim galaxies wrapped in oversized gravitational coats. In other cases, a few specific objects have sparked debate by appearing to have less dark matter than expected. One famous example is NGC 1052-DF2, which became controversial because measurements of its internal motions were interpreted by some as indicating an unusually low dark matter content. That claim is still debated. Distance measurements, velocity estimates, and observational uncertainties matter enormously when the object is faint and far away. Different research groups have argued over how strong the evidence truly is. In astronomy, especially at the edge of detection, disagreement is not a sign of failure. It is often the beginning of clarity. Even so, the existence of ultra-diffuse galaxies forces questions. How did they form without becoming brighter? Did they lose gas early, perhaps due to violent bursts of star formation that blew material outward? Were they shaped by environmental effects, such as interactions with larger galaxies, or the tidal forces within galaxy clusters? Did they form in unusually calm regions where star formation never efficiently took off? Or is there a piece of the galaxy formation story that simulations like the Millennium Simulation and the Illustris project still do not capture cleanly, especially when it comes to the messy physics of gas, feedback, and star formation? These questions matter because they sit right at the boundary between physics is understood and physics is still being negotiated. General relativity remains solid. The basic laws of motion remain solid. But the way those laws play out in complex systems across billions of years can still produce surprises. Ultra-diffuse galaxies are one of those surprises. They are not loud. They do not announce themselves with fireworks. They are easy to miss, which is almost part of the lesson. The universe can hide its strangest objects not behind distance, but behind faintness. Not behind drama, but behind subtlety. And once a few of these ghostly galaxies are found, another thought follows, quietly and inevitably. If the universe can produce objects like this and keep them stable and scatter them through cosmic space, what else might be out there at the edges of expectation? In a universe with hundreds of billions of galaxies, the improbable is not a glitch. It is a statistical certainty. But it still has the power to unsettle in the best possible way. because every time something faint and unlikely is confirmed to exist, the map of what is expected becomes a little more honest. Not because the universe is breaking its rules, but because it is showing how wide the rulebook really is. Ultra-diffuse galaxies have a way of forcing the mind to slow down because their strangeness is not flamboyant. They do not blaze. They do not explode. They simply sit there, spread thin across space, like a galaxy that forgot to finish becoming a galaxy. And once that faint silhouette is noticed, the next question arrives almost automatically, because it is the question that sits beneath so much of modern cosmology. What is holding them together? A galaxy is not just a collection of stars, it is a gravitational structure. Stars orbit within it, gas drifts through it, and over long timescales, everything is shaped by the gravity of the total mass. If a galaxy is large, the instinctive expectation is that its gravity is strong enough to keep it coherent. In the standard picture, much of that gravitational strength comes from dark matter, the unseen component that does not emit light but exerts gravity. Dark matter is not a small correction in modern cosmology. It is the scaffolding. The case for dark matter did not begin as a philosophical preference. It began as a mismatch. In the 20th century, astronomers measured how fast stars orbit within galaxies, and those speeds did not fall off the way they should if the only mass present was the visible mass. Vera Rubin's work on galactic rotation curves became especially famous because it made the problem impossible to ignore. In a simple Newtonian picture, orbital speeds should decrease farther from the galactic center. Much like planets in the solar system move more slowly the farther they are from the sun. But in many galaxies, stars far from the center orbit at roughly similar speeds to those closer in. Those flat rotation curves strongly suggest there is more mass than can be seen, distributed in an extended halo. That is one of the key observational pillars of cold dark matter theory, which then becomes embedded into the broader Lambda Cold Dark Matter model. With that context, the discomfort of certain ultra-diffuse galaxies becomes clearer. A galaxy that is physically large but has very few stars might still be perfectly stable if it sits inside a massive dark matter halo. In fact, one possible interpretation of some ultra-diffuse galaxies is exactly that. A dim galaxy could be a normal gravitational structure whose star formation never became efficient, leaving it wrapped in dark matter, but underlit in starlight. In that sense, ultra-diffuse galaxies could be strange mainly to human eyes, not to gravity. But then the story becomes more complicated because a few specific cases have flirted with the opposite idea. Instead of being dominated by dark matter, some ultra-diffuse galaxies have been described as having surprisingly little of it, based on measurements of the motions of their stars and star clusters. The galaxy known as NGC 1052-DF2 became a flashpoint for this debate. If a galaxy that large truly contains far less dark matter than expected, then the standard formation picture becomes strained, because dark matter is supposed to be the gravitational cradle within which the visible galaxy forms. It is important to treat this carefully, because astronomy is a science of inference. No one can pick up a galaxy, place it on a scale, and weigh it directly. Mass is deduced from motion. Velocities are measured from spectra. Distances are estimated from standard candles and other methods. For faint, diffuse objects, uncertainties can be substantial. Small changes in assumed distance can shift the inferred mass dramatically. Different research groups have reanalyzed the same data, argued over distance estimates, and debated whether the evidence truly implies an absence of dark matter, or merely reflects measurement limits and statistical noise. that debate in itself is not a flaw. It is the scientific process doing what it does best. When the consequences are large, the scrutiny becomes intense. Observations are repeated, methods are refined, and new instruments are brought to bear. The discussion can feel like tension, but it is often a sign that the stakes are real. It is a reminder that the universe is not obliged to be simple, even if simplicity is deeply convenient. Whether these particular galaxies are truly dark matter deficient or not, ultra-diffuse galaxies still press on an important point. Galaxy formation is not only about gravity, it is also about messy physics. Gas cools, collapses, and forms stars. Massive stars explode as supernovae and drive winds that can push gas outward. Radiation from star formation can heat surrounding gas and slow further collapse. In galaxy clusters, hot intracluster gas and tidal forces can strip material away. These processes are difficult to model in full detail. Simulations such as the Millennium Simulation and the Illustris project have become increasingly sophisticated, but they still rely on subgrid models for star formation and feedback because the relevant physics happens on scales far smaller than the simulation can resolve directly. Ultra-diffuse galaxies may therefore be telling a story about baryonic feedback, the collective term for how ordinary matter, especially stars and gas, influences itself through radiation, winds, and explosions. One plausible pathway is that an ultra-diffuse galaxy formed stars early. Then energetic feedback drove gas out, leaving behind a sparse stellar population, spread through a gravitational potential that remained. Another pathway is that a galaxy formed in a low-density environment and never accumulated gas efficiently enough to build a dense stellar disk. In dense environments like galaxy clusters, tidal interactions might puff up a galaxy, spreading its stars outward and lowering its surface brightness while stripping gas and shutting down star formation. Each of these possibilities is physically reasonable. The discomfort arises because the population as a whole and the extremes within it may not sit neatly within current expectations. The universe is offering objects that are not impossible, but awkward. The kind of awkward that makes researchers reopen their notebooks and adjust their assumptions. There is also a deeper reason these galaxies matter. Dark matter is not just a helpful idea, it shapes the entire cosmic history. In the Lambda Cold Dark Matter model, small clumps of dark matter form first, then merge into larger structures, pulling ordinary matter along with them. If certain objects genuinely lack dark matter while still resembling galaxies, it could imply unusual formation scenarios, or it could hint at limitations in how mass is inferred from motion. Or it could, in the most radical reading, invite alternatives to dark matter itself. One famous alternative framework is modified Newtonian dynamics, often called MOND, proposed by Mordechai Milgram. MOND attempts to explain galactic rotation curves by modifying the behavior of gravity at very low accelerations, rather than invoking unseen matter. MOND has had successes in fitting certain galaxy rotation curves, but it faces challenges in explaining galaxy clusters, the cosmic microwave background, and large-scale structure as comprehensively as the Lambda Cold Dark Matter model does. Still, its existence is a reminder that the story of gravity and mass on galactic scales is not only a matter of data, but also of interpretation. The universe supplies the measurements. Humans build the frameworks. And at this point, a subtle shift can happen in the mind. Ultra-diffuse galaxies begin as faint oddities, but they quickly become part of a much larger conversation about what is truly known and what is still provisional. Dark matter is widely accepted in mainstream cosmology because it explains multiple lines of evidence, from rotation curves to gravitational lensing to cosmic structure formation. Yet the nature of dark matter remains unknown. Decades of laboratory searches and astrophysical constraints have narrowed possibilities, but no definitive direct detection has yet settled the question. In a sense, modern cosmology is very confident about the gravitational effect of dark matter and still uncertain about its identity. That combination of confidence and uncertainty is where anomalies thrive. They do not need to overturn the model. They only need to press against its edges. From there, it becomes easier to appreciate why the universe can feel both orderly and strange at the same time. On the larger scales, the cosmic web forms with predictable statistical properties. On smaller scales, individual objects can carry the signature of chaotic histories, unusual environments, or rare interactions. A galaxy can be puffed up by tides, starved of gas, or stripped by its surroundings. The universe is lawful, but it is not tidy. And then, almost naturally, attention shifts from structures that are strangely faint and spread out to objects that are not faint at all, but are in motion in a way that feels almost defiant. Because gravity does not only hold things together, gravity also throws things. In the Milky Way, most stars follow long orbital paths around the galactic center. The speeds are substantial, often hundreds of kilometers per second, but they are typically bound. A star may wander far from the center and return again, like a slow cosmic commuter on an impossibly long commute. The galaxy is, in that sense, a gravitational home. Once a star belongs to it, it usually stays, but not always. Hypervelocity stars are stars moving so fast that they can escape the gravitational pull of their galaxy entirely. They are not simply fast stars. They are stars that have effectively been evicted. Their trajectories point outward into intergalactic space, where they may travel for billions of years with no galaxy to orbit, no spiral arms to pass through, no returning home. The first time this is heard, it can sound like a dramatic claim. A star flung out of a galaxy, as though the galaxy lost its grip. But it is real, and it is observed. Surveys such as the Sloan Digital Sky Survey have helped identify candidates, and follow-up observations refine their velocities and trajectories. These stars are rare, which is part of what makes them interesting. They represent unusual interactions, the kind that occur only under extreme circumstances. In many cases, the likely culprit is the supermassive black hole at the Milky Way's center, known as Sagittarius A star. A supermassive black hole is not merely a heavy object. It is an extreme gravitational environment. If a binary star system, two stars orbiting each other, wanders too close, the gravitational forces can tear the pair apart. One star may be captured into a tight orbit around the black hole, while the other is flung outward at enormous speed. This general class of scenario is connected to what is known as the Hills mechanism, named after Jack Hills, who proposed this kind of interaction as a way to produce stars moving at extreme velocities. There are other possibilities as well. Interactions with a binary black hole, or the aftermath of certain supernova explosions in binary systems, can also create high-speed stars. But the common theme is the same. Hypervelocity stars are born from rare gravitational chaos, moments when the usual gentle clockwork of stellar orbits is interrupted by a close encounter with something massive and unforgiving. They represent a different kind of anomaly than ultra-diffuse galaxies. Ultra-diffuse galaxies challenge formation efficiency and mass distribution. Hypervelocity stars challenge dynamical expectations. They are not about faintness and subtlety. They are about motion so extreme that a star can cross the boundary between being bound and unbound, between belonging to a galaxy and being cast into the dark between galaxies. In a way, they are a reminder of something that is easy to forget when thinking of gravity as a glue. Gravity is also a slingshot. It can accelerate, redirect, and expel. The same physical law that holds planets in orbit can, under the right conditions, fling a star outward faster than the galaxy can hold it. And in the quiet logic of astrophysics, that matters, because it means the universe is not only assembling structures, it is also constantly reshaping them, removing pieces, redistributing matter, and creating wandering objects that carry information about violent interactions long after the event itself has faded from view. A hypervelocity star is, in a sense, a moving fossil. Its speed tells a story about a past encounter, likely near a supermassive black hole, where gravity operated at its most dramatic. The star continues on, long after the original interaction, carrying that story into the deep. So the narrative widens again. Ultra-diffuse galaxies hint that some structures form in ways that are unexpectedly inefficient or unexpectedly fragile. Hypervelocity stars show that even when structures exist, their contents can be forcibly rearranged. The galaxy is not a sealed system. It is a dynamic place, and the rarest events can leave the clearest signatures. In a universe governed by predictable laws, it is often the outliers that teach the most. They reveal the strength of a theory by showing how far it can stretch before it begins to feel strained. They also offer a quiet kind of humility. Not everything that happens often will be seen, but what is seen, even rarely, is enough to remind anyone listening that the universe is large enough to produce outcomes that feel almost like exceptions. Not exceptions to physics, exceptions to comfort. A hypervelocity star does not look unusual at first glance. It is not necessarily brighter than its neighbors. It does not carry a visible warning label saying, "recently ejected." The difference is in its motion, in the quiet fact that it is traveling so fast that the Milky Way cannot keep it. To understand how that can happen, it helps to stop thinking of a galaxy as a gentle spiral and start thinking of it as a gravitational landscape, full of steep valleys and sudden drop-offs. Near the center of the Milky Way sits Sagittarius A star, the supermassive black hole with a mass of about 4 million suns. In most parts of the galaxy, gravity is spread out across billions of stars and a vast dark matter halo. Near Sagittarius A star, gravity is concentrated into a compact region. The gravitational field becomes intense, and the tidal forces, meaning the difference in gravitational pull across an object, becomes strong enough to pull systems apart. This is where the Hills mechanism comes in, proposed by the astrophysicist Jack Hills. Imagine a binary star system, two stars orbiting each other in a stable dance. In the calm outskirts of the galaxy, that dance can continue for billions of years. But if that pair wanders too close to a supermassive black hole, the encounter becomes a three-body problem. In physics, three-body interactions are famously chaotic, not because the laws are unknown, but because tiny differences in initial conditions can lead to very different outcomes. The black hole's gravity can disrupt the binary. One star can lose energy and be captured into a tight orbit around the black hole. The other can gain energy and be ejected at tremendous speed. That trade of energy is the key. The system does not create energy from nothing. It redistributes energy among its members. A star that becomes tightly bound to the black hole ends up in a deeper gravitational well, meaning it has given up energy. The ejected star receives that energy as kinetic energy, speed. If the ejection speed is high enough, the star becomes unbound from the galaxy, turning into a hypervelocity star that travels outward into intergalactic space. The Hill's mechanism is one of those ideas that feels almost too neat, like a cosmic trick, but it fits the physics and it fits many observations. It also explains why hypervelocity stars are rare. They require a specific sequence of events. A binary system must exist. It must be perturbed into a trajectory that carries it close to the galactic center. It must pass close enough to Sagittarius A star for disruption to occur, yet not so close that both stars are swallowed. That is a narrow target in a galaxy of immense size, which means the universe can produce hypervelocity stars, but not in huge numbers. There are variations on the theme. If a galaxy contains a binary supermassive black hole, perhaps after a galactic merger, the ejection process can be even more efficient. Supernova explosions in close binary systems can also fling stars away at high speeds, though typically not as extreme as Hill's mechanism ejections. But the central idea remains that gravity can both bind and expel, depending on geometry, timing, and proximity. Hypervelocity stars therefore act as messengers from the most extreme environment in the Milky Way. Their motion provides evidence that powerful gravitational interactions are not just theoretical. They happen. They leave survivors. They produce objects that carry a dynamical signature across the galaxy. Once that is appreciated, it becomes natural to keep following gravity inward, deeper into the realm where ordinary intuition starts to fray. The same force that can fling a star out of a galaxy can also crush matter into forms that barely resemble the material of everyday life. A star like the Sun is held up by heat and pressure, produced by nuclear fusion. When that fuel runs low, the story changes. Gravity begins to win. The star's core contracts. Depending on the original mass, the star may leave behind a white dwarf, a neutron star, or a black hole. These are not merely dead stars. They are new physical regimes, where matter is compressed to extraordinary densities, and where quantum physics becomes as important as gravity. Neutron stars, in particular, represent one of the most extreme stable forms of matter known. They are typically about the mass of the Sun or more, compressed into a sphere roughly the size of a city, on the order of tens of kilometers across. The density is almost beyond comprehension. A single teaspoon of neutron star material would weigh about 1 billion tons on Earth. That number can be hard to hold in the mind, so it helps to compare it. It is similar to taking a mountain's mass and placing it into the volume of a small building. The result is matter packed so tightly that electrons and protons are squeezed together, forming neutrons. The concept of neutron degeneracy pressure helps explain how such an object can resist total collapse. In quantum mechanics, certain particles cannot all occupy the same quantum state. This is related to the Pauli exclusion principle. In a white dwarf, electron degeneracy pressure provides support against gravity. In a neutron star, neutron degeneracy pressure plays a similar role, along with additional strong nuclear forces that become important at these densities. But neutron stars do not all behave the same way. Some are discovered as pulsars, spinning rapidly and emitting beams of electromagnetic radiation. Others are quieter. And then there is a rare and unsettling subclass that seems to take everything about neutron star physics and turn the intensity dial much higher. Magnetars. Magnetars are neutron stars with magnetic fields so strong that they are difficult to describe without sounding as though exaggeration has slipped in. Their field strengths can reach about 1,000 trillion Gauss. For comparison, Earth's magnetic field is about half a Gauss. A typical refrigerator magnet is on the order of 100 Gauss. The magnetic field around a magnetar is not just stronger by a small factor. It is stronger by a scale so large that ordinary comparisons become almost comical, like comparing a candle to the brightness of the sun. The magnetar model was developed in the 1990s by Robert Duncan and Christopher Thompson, who proposed that some neutron stars could be born with exceptionally strong magnetic fields, and that the decay and rearrangement of those fields could power dramatic bursts of high-energy radiation. Observationally, magnetars are linked to phenomena called soft gamma repeaters and anomalous X-ray pulsars. These are sources that emit repeated bursts of gamma rays or persistent X-ray emission that cannot be explained by the usual rotation-powered pulsar mechanism alone. When a magnetar releases energy, it can do so through starquakes. The crust of a neutron star is not like Earth's crust, but it can still fracture under stress. Magnetic fields in a magnetar can twist and strain the crust and the magnetosphere. And when that stress is released, a burst of radiation can occur. NASA missions such as the Swift Observatory have detected magnetar bursts, and other space-based X-ray and gamma-ray telescopes have contributed to building the observational picture. The sheer strength of a magnetar's magnetic field is not only an astrophysical curiosity. It pushes into regimes where magnetic forces affect matter itself in unusual ways. In extremely strong fields, the behavior of atoms changes. Electron orbitals can become elongated and the structure of matter can become anisotropic, meaning it behaves differently depending on direction. These are not the conditions found in laboratories on Earth. They are conditions that make the universe feel like it contains hidden corners, where physics is still physics, but it looks unfamiliar. At this point, it becomes clear why magnetars can feel like objects that should not exist. Not because they violate known laws, but because they occupy an extreme end of what those laws permit. They are the cosmic equivalent of a pressure test. If neutron stars are already a demonstration of matter compressed to the edge of stability, magnetars are neutron stars with an added layer of intensity, where magnetic energy becomes a dominant force. This leads naturally into the deeper question: how does physics describe matter at these densities? Where, exactly, are the limits? Neutron star theory is full of thresholds. One of the most famous is the Tolman-Oppenheimer-Volkoff limit, derived from work by Richard Tolman, J. Robert Oppenheimer, and George Volkoff. This limit describes the maximum mass a neutron star can have before it can no longer support itself against collapse, at which point it becomes a black hole. The exact value of the limit depends on the equation of state of neutron star matter, meaning the relationship between pressure and density. And that equation of state is one of the great uncertainties in astrophysics, because it depends on the behavior of matter under conditions of extreme density, where the strong nuclear force and potentially exotic forms of matter become important. At neutron star densities, protons and neutrons may behave in unexpected ways. There are ideas involving superfluid neutrons, superconducting protons, and the possible presence of more exotic components such as hyperons, which are particles containing strange quarks. Some models even consider the possibility of quark matter, where the distinction between individual protons and neutrons dissolves into a sea of quarks. These possibilities are explored using the framework of quantum chromodynamics, the theory that describes how quarks interact through the strong force. The challenge is that while quantum chromodynamics is well established, calculating the behavior of matter in this dense regime is extraordinarily difficult. Neutron stars therefore become natural laboratories. Observations of their masses, radii, and spins provide constraints that narrow down what the equation of state can be. One mission designed specifically for this is NISA, the Neutron Star Interior Composition Explorer, operating on the International Space Station. NISA measures X-ray emissions from neutron stars and uses detailed modeling to infer properties such as radius. These measurements help constrain how stiff or soft neutron star matter must be, which in turn influences the maximum mass and structure of these objects. Magnetars add another complication. Their magnetic fields can influence the outer layers of the star and the behavior of charged particles in the magnetosphere. Their bursts and timing behavior provide additional data. They are not just exotic curiosities. They are measurements waiting to be interpreted. So the narrative tightens further. From galaxies where the questions revolve around dark matter and formation efficiency, to hypervelocity stars where gravity redistributes energy through rare close encounters, to neutron stars and magnetars, where gravity and quantum physics share the stage in the densest stable matter known. There is a strange coherence to it. The same gravity that shapes a galaxy's spiral arms can also tear a binary star apart at the galactic center. The same physical laws that allow a star to shine for billions of years can also end its life by crushing its core into a city-sized object weighing more than the sun. And then, in a small fraction of cases, that crushed remnant is born with a magnetic field so intense that it becomes one of the most extreme objects ever observed. These objects exist because the universe has time, volume, and opportunity. It can run experiments endlessly. It can produce the typical outcome most of the time, and still occasionally produce a rare and extreme result. The surprise is not that it happens. The surprise is that it happens often enough for human instruments to catch it. And once the mind has followed this path inward into the deep pressures and strange magnetism of neutron stars, it becomes easier to accept that the universe may contain other objects that feel equally uncomfortable, perhaps even older, perhaps formed in conditions more alien than any star's interior. Because there is one place where the universe was denser than a neutron star, hotter than a magnetar's surface, and more chaotic than any three-body encounter near a black hole. The early universe itself. A supermassive black hole at the center of a galaxy can feel like the ultimate gravitational authority, a deep well that shapes the motion of stars for tens of thousands of light years around it. But even that kind of black hole is, in a sense, a late arrival. It forms after stars have lived and died. It grows through mergers, accretion, and time. It belongs to a universe that already has galaxies, already has chemistry, already has structure. Now imagine a different kind of black hole. One that did not wait for stars. Primordial black holes are a possibility that lives close to the beginning of everything, back when the universe was young enough that the usual categories like galaxy and star and planet had not even become meaningful yet. The word primordial is the clue. It points to an era when the universe was not a landscape of separate objects, but a hot, dense, expanding state where matter and radiation were mixed almost everywhere. In that earliest time, the universe was expanding and cooling, and its contents were remarkably uniform. Not perfectly uniform, though. Tiny variations in density existed, and those variations mattered. They were the seeds that would eventually become the cosmic web, the galaxies, the stars, and everything built from them. Most of those variations were small enough that they simply grew slowly under gravity, becoming today's structure over billions of years. But the idea behind primordial black holes is that some density variations might have been unusually large. Not large enough to create a galaxy right away because galaxies require cooling gas and long timescales, but large enough that a region could collapse under its own gravity almost immediately, forming a black hole in the early universe. This is not the usual story of black holes. The familiar pathway is stellar death. A massive star runs out of fuel, its core collapses, and a black hole forms. Primordial black holes, by contrast, would be black holes born from the universe's earliest unevenness, without any star involved. Stephen Hawking explored this possibility in the 1970s, including the profound idea that black holes are not completely black. In quantum physics, the vacuum is not truly empty. Fluctuations can occur, and near the event horizon of a black hole, those fluctuations can lead to what is now called Hawking radiation. For stellar mass black holes, Hawking radiation is far too weak to matter over the current age of the universe. But for extremely small black holes, it becomes important. A small enough black hole would evaporate over time, losing mass as it radiates. That creates an immediate and useful thought. If primordial black holes formed across a range of masses, the smallest would not survive to the present day. They would evaporate away. Only those above a certain mass threshold would still be around now. So even before looking for them, theory already suggests that the surviving population, if it exists, would be limited by evaporation. And then comes the deeper question. If primordial black holes do exist, how could anyone know? Black holes do not shine. They do not advertise. They do not carry a label saying where they came from. Their existence is inferred through their gravitational effects and, in some cases, through the radiation produced by matter falling into them. For primordial black holes, the challenge is that many of them might be isolated, without bright accretion disks, drifting through the darkness and doing their gravitational work quietly. So the search becomes indirect. It becomes a kind of cosmic detective work. One approach is gravitational lensing. Mass bends light, a prediction of general relativity that has been confirmed countless times. If a compact object passes between an observer and a distant star, it can briefly magnify that star's light. This is called gravitational microlensing. It does not require the lensing object to emit light. It only requires mass. Large observational campaigns have looked for these subtle lensing events. The hope is that a population of compact objects, including primordial black holes in certain mass ranges, would reveal itself statistically through microlensing rates. Another approach comes from gravitational waves. The laser interferometer. Gravitational Wave Observatory has detected mergers of black holes with masses that sparked interesting discussions, because some events involved black holes heavier than what had been considered typical for certain stellar evolution pathways. It is important to be cautious here. Stellar evolution has more flexibility than early simplified models suggested, and black hole masses can vary depending on metallicity, mass loss, and binary interactions. Still, the fact that gravitational wave astronomy now observes black hole populations directly raises an intriguing possibility. If a primordial black hole population exists, some mergers might include primordial black holes, especially if they formed binaries in the early universe or were later captured into pairs. That does not mean any specific detected merger must involve primordial black holes. It simply means the observational door is open in a new way, and the universe has started offering a fresh set of clues. But to ground all of this properly, it helps to step even further back and talk about what the early universe was doing in the first place. Because primordial black holes, if they exist, are not just objects. They are fossils of conditions that existed long before galaxies. One of the central ideas in modern cosmology is inflation, proposed in influential form by Alan Guth. Inflation is the hypothesis that the universe underwent an extremely rapid expansion very early in its history, smoothing out large-scale irregularities while also generating tiny fluctuations. These fluctuations are crucial. They are not a minor detail. They are the origin of structure. In the inflationary picture, quantum fluctuations in the early universe are stretched to cosmic scales, becoming the slight density variations that later grow into galaxies and clusters. Those variations are not imagined, they are observed. The cosmic microwave background is the afterglow of the early universe, the light released when the universe cooled enough for electrons and protons to combine into neutral hydrogen, allowing photons to travel freely. That ancient light is remarkably uniform, but it contains tiny temperature differences across the sky. Those differences correspond to density fluctuations in the early universe. They were mapped with extraordinary precision by missions including the Planck satellite. This matters for primordial black holes because the cosmic microwave background is, in effect, a measurement of the early universe's smoothness. If density fluctuations had been too large on certain scales, the cosmic microwave background would look different. It would show stronger irregularities. It would carry signatures of early collapse. That means the cosmic microwave background places constraints on how extreme the early density fluctuations could have been, which in turn limits how many primordial black holes could have formed. The same is true for other cosmological observations. Primordial black holes, depending on their abundance and mass, could influence the formation of structure, the rionization history of the universe, and the background radiation fields. Even without direct detection, their presence would leave fingerprints. The universe is not only a place where objects exist, it is also a record of what has influenced it. So the idea of primordial black holes sits in a fascinating position. It is speculative in the sense that it is not confirmed, but it is not arbitrary. It is shaped by well-tested physics. It must be compatible with general relativity, with inflationary cosmology, with the measured properties of the cosmic microwave background, and with the observed distribution of matter in the universe. In other words, primordial black holes are not a wild guess. They are a constrained possibility. There is also a quiet reason this possibility keeps returning. Dark matter remains one of the great unknowns. The Lambda Cold Dark matter model works extraordinarily well on large scales, but it does not specify what dark matter is made of. Many candidates have been proposed. Primordial black holes are sometimes discussed in that context as a potential contributor to dark matter in certain mass windows. Again, this is not a free choice. Observations rule out many mass ranges as a dominant component, but the idea persists in limited forms because it offers a different kind of dark matter candidate. One made not of new particles, but of gravitational relics from the early universe. That framing also highlights an important boundary. Even if primordial black holes exist, they may not explain all of dark matter. They may be a small fraction, they may be rare, they may be confined to narrow mass ranges. The universe often prefers mixtures over single explanations. And there is something quietly humbling about that. The earliest moments of the universe are not accessible in a direct, everyday way. No telescope can take a photograph of the first instant. Yet, through the cosmic microwave background, through gravitational waves, through lensing surveys, and through the mathematics of inflation, cosmologists can place limits on what could have happened. They can narrow the list of possibilities. Primordial black holes, if they are real, would be among the oldest compact objects in existence. They would be older than stars, older than galaxies, older than anything that has ever burned or cooled in the usual sense. They would be gravitational artifacts from a time when the universe was still deciding what kind of universe it was going to become. And whether they are ultimately confirmed or ruled out, the search itself does something valuable. It ties the existence of a black hole, an object that feels like the end point of stellar evolution, to the beginning of cosmic history. It reminds the mind that the universe is not only a place of things, it is a story of conditions. The objects seen today are echoes of the earliest rules, the earliest fluctuations, the earliest moments of imbalance that later became everything. In that light, a primordial black hole is not only a strange object that may exist, it is a question mark left behind by the beginning. Once the mind has wandered back to the early universe, it can feel natural to think of cosmic history as a kind of grand sequence. First, the hot beginning. Then the first atoms. Then the first stars. Then galaxies. Then planets. A tidy story arranged like a timeline in a textbook. Real astronomy is not so neat. The universe does not simply build one layer and then move on. It builds, breaks, rearranges, and repeats. Some objects that seem as though they belong late in the story can end up appearing in unexpected places, and some objects that seem as though they should be common can turn out to be elusive. Even something as familiar sounding as a planet can become part of the catalogue of cosmic oddities when it refuses to behave like a planet is supposed to behave. A planet, in most people's mental picture, has a star, a sun to orbit, a source of warmth and light, a central anchor that gives the planet its role in a system. But the galaxy also contains rogue planets, sometimes called free-floating planets, objects with planetary mass that drift through space without an obvious host star. They do not orbit in the usual way because there may be nothing luminous to orbit. They are the cosmic equivalent of a door key with no door, or a moon that never found a planet. The first reaction is often to wonder if they are rare, or if the term is being used loosely. But there is real evidence that such objects exist, and the evidence comes from a method that is almost perfectly suited to finding things that do not emit light. Gravitational microlensing. When a compact object passes in front of a distant background star, its gravity bends and focuses the light, briefly magnifying the star. The lensing object can be dim or even invisible. It still reveals itself through its mass. Collaborations such as OGLE, the Optical Gravitational Lensing Experiment, and MOA, the Microlensing Observations in Astrophysics project, have spent years watching dense star fields for these subtle brightening events. In some microlensing detections, the lensing mass appears to be in the planetary range, and there is no clear sign of an accompanying star. That suggests a free-floating planet, or at least a planet on an extremely wide orbit that makes the host star effectively irrelevant to the lensing signature. There are multiple ways to create such an object. One is ejection. Planet formation begins in a disk of gas and dust around a young star. Over time, growing planets interact gravitationally with each other. In many systems, especially those with multiple giant planets, those interactions can become chaotic. Orbits shift, objects scatter. A planet can be flung outward, and if it gains enough speed, it can leave the system entirely. That is not fantasy. It is the same gravitational logic behind hypervelocity stars, only at a different scale. Gravity does not care what kind of object it is moving around. A planet can be ejected just as surely as a star if the encounter is energetic enough. Another possibility is that some rogue planets form more like failed stars, by direct collapse in a molecular cloud fragment that never grows massive enough to ignite nuclear fusion. In that case, the boundary between a planet and a brown dwarf becomes relevant. A brown dwarf is an object too small to sustain hydrogen fusion like a star, but in some cases, massive enough to fuse deuterium early in its life. The line between the largest planets and the smallest brown dwarfs is not purely about mass. It is also about formation history. Did it form in a disk, like a planet, or did it collapse directly, like a star? Astronomers care about that distinction because it changes what the object means. A planet ejected from a system suggests violent dynamical history. A planet formed in isolation suggests something more fundamental about how clouds fragment and what masses those fragments can naturally produce. The unsettling part is that some estimates suggest rogue planets might be numerous, potentially comparable in number to stars, though the uncertainties remain large. Micro-lensing surveys have detection biases and limited sampling. It is very easy to miss a cold, dark object drifting alone. That means the true population could be smaller than some early estimates suggested, or it could be larger in certain mass ranges. What is clear is that the existence of rogue planets broadens the mental image of what a planet can be. A planet is not always a companion. Sometimes it is a wanderer, and there is something quietly haunting about that. A planet-sized object traveling through interstellar space with no sunrise, no stellar warmth, just a slow drift through darkness. It is not an object designed to be seen, yet gravity, once again, makes it detectable. From there, it is a small step to another kind of boundary question. If a rogue planet challenges intuition about what a planet is supposed to do, there is a parallel question about stars. What is a star supposed to be allowed to become? Stars form from gravitational collapse in molecular clouds, and for a star to ignite hydrogen fusion, it must reach a certain core temperature and pressure. Once fusion begins, an entirely different kind of limit becomes important. Light itself becomes a force. Radiation pressure pushes outward, and as a star becomes more luminous, radiation pressure increases. In very massive stars, that outward push can become strong enough to counter gravity, potentially limiting how massive a star can become while still remaining stable. One of the classic ideas tied to this is the Eddington limit, named after Arthur Eddington. The Eddington limit describes a balance point where the outward force from radiation pressure equals the inward force of gravity for a star's outer layers. If a star's luminosity exceeds that limit in a simple model, it might begin shedding mass through intense stellar winds because its own light effectively pushes its outer material away. For a long time, this contributed to the belief that there was an upper mass limit for stars, on the order of perhaps 100 to 150 times the mass of the Sun. Not because physics forbids larger masses absolutely, but because the processes of formation and stability become increasingly difficult as radiation pressure intensifies. A forming star grows by accreting gas. If the developing star becomes too luminous too early, it can blow away the surrounding gas and cut off its own growth. And then astronomers found stars that appear to be heavier than that comfortable limit. One striking example is R136A1, located in the Large Magellanic Cloud in the star-forming region known as R136. This object is often cited as among the most massive known stars, with estimates that have placed its initial mass at well over 100 times the mass of the Sun, and in some analyses closer to 200 or even higher. As with many extreme astrophysical objects, the precise value depends on modeling, including assumptions about stellar winds, metallicity, and evolutionary stage. But even allowing for uncertainty, these stars press against the upper boundary, where formation becomes difficult. The challenge is not merely keeping such a star stable after it forms. The challenge is forming it in the first place. To build an extremely massive star, a molecular cloud must feed it with enormous amounts of gas, quickly enough that the star can grow before feedback processes halt accretion. Massive stars emit intense ultraviolet radiation. They drive powerful winds. They ionize their surroundings, heating gas and making it harder to collapse. In many cases, they carve out bubbles in their natal clouds. That is part of why massive star-forming regions glow so brightly in nebular emission. They are energetic, disruptive environments. So how does a star reach such an extreme mass, despite those forces? Several mechanisms have been proposed. One possibility is that extreme massive stars form in very dense stellar clusters, where gas is abundant and accretion flows can be channeled effectively. Another possibility is stellar mergers. In a crowded cluster, massive young stars can collide and merge, creating a single star with a larger mass than typical formation pathways would allow. In that case, the object is not a straightforward result of accretion, but the product of dynamical interactions, a kind of cosmic shortcut that builds a heavyweight by combining multiple heavyweights. The environment matters too. Metallicity, meaning the abundance of elements heavier than helium, influences stellar winds. Lower metallicity stars tend to lose less mass through winds, allowing them to remain more massive. That means the early universe with lower metallicity overall may have produced even more extreme stellar masses. This connects, intriguingly, back to the first generation of stars, which are often modelled as more massive on average than modern stars, though direct observations of those earlier stars remain out of reach. Even in the present universe, however, stars like R136A1 remind astronomers that upper limits in nature are sometimes better understood as regions where the universe rarely goes, but can. That is why they belong in the same family as rogue planets. Both challenge tidy categories. Both reveal that gravitational formation processes can produce outcomes that feel like outliers. A planet without a star drifting through space. A star so massive that it strains the idea of how it could assemble without tearing its own birthplace apart. And the deeper theme remains consistent. These objects do not require new physics to exist. They require the universe to be big enough and chaotic enough and patient enough that even the rare outcomes have time to happen. There is also something quietly useful in these extremes. Rogue planets tell astronomers about the dynamical history of planetary systems and the efficiency of planet formation. Extremely massive stars inform models of stellar feedback, chemical enrichment, and the formation of black holes. Massive stars are the ones that live fast, die young, and seed the interstellar medium with heavier elements. Their winds and supernovae shape future star formation. If the upper mass limit is flexible, then the universe's chemical and energetic evolution may be shaped by these rare giants more than their numbers would suggest. So the story broadens again, not by moving farther outward, but by widening the definition of what normal formation pathways can produce. Planets can be cast out. Stars can push past comfortable limits. Gravity remains the central sculptor, but it works through environments, interactions, and chance. And if the universe can produce an object that is almost too massive to assemble, or a planet that drifts without a sun, it becomes easier to accept that there may be other objects that appear strange for different reasons. Not because gravity failed, but because the universe sometimes chooses the rare path, simply because it has the space and time to do so. Some cosmic oddities sit quietly in the dark, like ultra-diffuse galaxies that barely glow or rogue planets that drift without a star. Others announce themselves with the briefest flash, a moment so short that it can feel as if the universe is tapping the observer on the shoulder, then vanishing before anyone has time to ask why. Fast radio bursts belong to that second category. A fast radio burst, often shortened to FRB, is exactly what it sounds like. A burst of radio waves extremely bright and extremely brief. The duration is typically on the order of milliseconds, which is to say, the blink of an eye is leisurely by comparison. Yet in that tiny slice of time, an FRB can release an enormous amount of energy in radio wavelengths. The energy implied can be comparable to what the sun emits over days, concentrated into a flash so quick that it often appears in data as a single spike. The first widely discussed FRB was discovered in archived data and became known as the Lorimer burst, after Duncan Lorimer, one of the scientists involved in identifying it. At the time, it was not immediately obvious what it was. A single burst could be a glitch, interference, or something closer to home. The sky is full of artificial radio signals, and radio astronomy has to fight constantly against human noise. But more bursts were found, and as the catalogue grew, a pattern emerged that made the phenomenon difficult to dismiss. These were not local artifacts. They showed signs of having travelled through vast stretches of ionized gas. One of the key clues is dispersion. Radio waves travelling through a plasma, such as interstellar or intergalactic medium, are slowed slightly, with lower frequency waves delayed more than higher frequency waves. This produces a characteristic sweep in time across frequencies. By measuring the dispersion, astronomers can estimate how much plasma the signal has passed through, which provides hints about distance. Many FRBs show dispersion measures consistent with extragalactic origin. In plain terms, they look as though they have crossed intergalactic space. That immediately makes the energy problem sharper. A signal that bright, coming from outside the Milky Way, must be produced by something extremely energetic. For a while, FRBs were treated as one-time mysteries. If an event happens once, it could be a catastrophic explosion or collision. But then a second category appeared: repeating fast radio bursts. The existence of repeaters changed the entire conversation. A repeating source cannot be a one-time destruction event, at least not in the simplest sense. It must be capable of producing multiple bursts without annihilating itself. That constraint narrows the list of plausible engines dramatically. One of the major modern instruments driving FRB discovery is CHIME, the Canadian Hydrogen Intensity Mapping Experiment. CHIME was built with cosmology and large-scale structure studies in mind, but its wide field of view and continuous monitoring made it a powerful FRB hunter. CHIME has found large numbers of bursts, including repeaters, and has helped reveal that FRBs are not a single oddity, but a population. So what produces them? The leading explanations involve compact objects, neutron stars, magnetars, and in some models, interactions involving black holes or highly magnetized plasma environments. The magnetar connection became especially compelling after an event in the Milky Way provided a kind of rare calibration point. A known magnetar, called SGR 1935+2-154, produced a radio burst that resembled an FRB, though less energetic than the extragalactic ones. The fact that a magnetar could produce an FRB-like signal suggested that at least some FRBs might be powered by magnetar activity. It is not a complete solution because not every FRB neatly fits a single model, and the diversity of observed behaviors, including repeating patterns, burst energies, and environments, suggests there may be multiple pathways. Some FRBs occur in star-forming galaxies. Others occur in older environments. Some repeat frequently. Others have not been seen to repeat at all. The field is active, cautious, and still full of open questions. And that is part of why FRBs feel like they should not exist. Not because they are forbidden, but because they are brief enough and intense enough that they force the mind to confront how much can happen in a millisecond. They also highlight a timing problem in observation itself. If a telescope is not looking at the right place at the right instant, the burst is missed. That means the true number of FRBs could be far larger than what has been observed so far. The universe could be flashing more often than anyone realizes. This also makes them strangely intimate. Unlike galaxies and stars that can be studied steadily, an FRB is a fleeting event. It is a cosmic transient, a reminder that the sky is not static. It is alive with short-lived signals that can vanish as quickly as they appear. From this kind of transient, the mind can shift to a different kind of timing problem, one that is almost the opposite. Not a millisecond flash, but a growth process that seems to require more time than the universe had available. This is where the discussion turns to black holes that grew too fast. In the modern universe, supermassive black holes sit at the centers of many galaxies, including the Milky Way. Their masses can range from millions to billions of times the mass of the Sun. Over cosmic time, they grow by accreting gas and by merging with other black holes. That seems straightforward, at least in outline. Time is abundant. Galaxies have billions of years to feed their centers. The discomfort comes when extremely massive black holes are observed in the early universe, at epochs when the universe itself was still relatively young. Observations of distant quasars discovered in surveys such as the Sloan Digital Sky Survey and now extended by the James Webb Space Telescope reveal supermassive black holes shining brightly when the universe was less than 1 billion years old. A quasar is powered by accretion. Gas falling toward a black hole forms an accretion disk, heats up through friction and compression, and emits enormous amounts of light, often outshining the entire host galaxy. The brightness allows quasars to be seen across immense distances. That visibility, however, comes with a puzzle. If a quasar is shining that brightly, the central black hole must already be massive. So how did it get that way so quickly? One limit often discussed in this context is the Eddington accretion limit, linked to the same Arthur Eddington whose work relates to radiation pressure in stars. The idea is similar. As gas falls into a black hole and radiates energy, that radiation exerts pressure outward. If the luminosity becomes too high, it can push back on infalling matter and limit the rate of accretion. Under typical assumptions, accretion at around the Eddington limit leads to a characteristic exponential growth timescale, often associated with the Salpeter time, named after Edwin Salpeter. This sets a pace for how quickly a black hole can grow if it is shining efficiently. If a black hole starts small, say the remnant of a massive star, it must grow through many folding times to reach billions of solar masses. That can be done, in principle, but it requires sustained near maximal accretion over long periods without interruption. In a real early universe with feedback, turbulence, and evolving galaxies, that kind of uninterrupted feeding can be hard to arrange. This has led to the idea that early supermassive black holes may have started with larger seeds. Instead of beginning as a stellar remnant of tens of solar masses, perhaps some black holes form through direct collapse of massive gas clouds, creating seed black holes of thousands or even hundreds of thousands of solar masses. Another possibility is that dense star clusters experienced runaway collisions and mergers, producing an intermediate mass black hole that then grew further. There are also models in which early accretion can briefly exceed the Eddington limit under certain conditions, allowing faster growth, though such phases must still be consistent with feedback and observed quasar properties. The James Webb Space Telescope has intensified interest in this puzzle because it has the sensitivity to observe galaxies and active nuclei at very high redshifts. Some early galaxies appear massive and mature earlier than expected, and some active black hole candidates appear in systems that look surprisingly developed for their cosmic age. It is important to keep the discussion grounded. Measurements at these distances are challenging. Interpreting galaxy masses and black hole growth rates depends on modeling and assumptions about stellar populations, dust, and emission mechanisms. Some early claims evolve as datasets improve. Even so, the core timing tension remains. The universe appears to host very massive black holes at times when conventional growth pathways feel tight on time. In a way, this is the same kind of discomfort seen elsewhere, just expressed differently. Ultra-diffuse galaxies challenge efficiency. Hypervelocity stars challenge dynamics. Magnetars challenge extremes of matter and magnetic field. Primordial black hole candidates challenge early conditions. Fast radio bursts challenge transient intensity. Early supermassive black holes challenge growth timescales. These are all timing problems in different costumes. Fast radio bursts force the question of what can release immense energy on a timescale shorter than a heartbeat. Early quasars force the question of what can build a billion solar mass black hole while the universe is still young by cosmic standards. And both remind anyone listening that astronomy is not only about what exists, it is also about when it exists and how quickly it can happen. The universe has a schedule that sometimes feels almost too ambitious, producing extremes either in a flash or in a rush, and leaving scientists to piece together the hidden sequence of events that made the outcome possible. The sky, seen from the ground, looks steady. Stars rise and set. The Milky Way drifts overhead. But the deeper reality is that the universe is constantly doing things on timescales ranging from milliseconds to billions of years. Sometimes it does them faster than anyone expected. The dark matter story is, in many ways, a story about confidence built on multiple lines of evidence. Galaxies rotate too fast for their visible mass. Galaxy clusters hold together more tightly than their starlight suggests. Gravitational lensing maps show mass where there is little or no luminous matter. On the larger scales, the distribution of galaxies across the universe fits the patterns produced when cold, dark matter is included in simulations of cosmic structure formation. That convergence is why dark matter has become such a central piece of modern cosmology. And yet, for all that confidence, dark matter remains unseen. It is inferred, not photographed. It is measured through what it does, not through what it is. That leaves a very specific vulnerability in the story. If an object appears to behave as though it has little or no dark matter, it does not merely add another curiosity to the catalogue. It presses directly on the method by which the invisible is inferred. This is why the debate around certain galaxies described as having unusually little dark matter has carried such weight. The discussion is not about a single object being odd. It is about whether the scaffolding itself can be absent while the building still stands. One of the best-known examples is NG C1052-DF2, along with its close companion in the conversation, NG C1052-DF4. These galaxies are often discussed in the context of ultra-diffuse galaxies, but the specific claim that drew attention was stronger than faintness. The claim was that their internal motions, inferred from the velocities of globular clusters and stars, suggested a total mass not much larger than the mass of their visible matter. In other words, they appeared to be lacking the extra gravitational pull that dark matter is expected to provide. If that were straightforwardly true, it would raise immediate questions. In the standard Lambda Cold Dark Matter model, galaxies form inside dark matter halos. The halo is not an optional accessory. It is the deep gravitational well into which gas falls, where stars then form. A galaxy without a halo would be like a river without a valley. Not impossible in principle, but difficult to create in the usual way. But astronomy rarely allows simple declarations, especially when the object is faint and the measurements are delicate. The estimated mass of a galaxy depends strongly on how far away it is, and distance is not always easy to measure precisely. A small revision in distance can change the inferred size, brightness, and mass. Velocity measurements depend on the quality of spectra and the number of tracers available. With only a handful of globular clusters, statistical scatter can become significant. Different research groups have reanalyzed the data, proposed different distance estimates, and argued about whether the evidence truly implies a dark matter deficiency or whether it can be reconciled with more conventional expectations. This back and forth can sound like uncertainty, but it is actually a kind of careful honesty. When the claim touches something foundational, the burden of proof rises. Every assumption gets checked. Every method gets stress-tested. That is how a scientific community protects itself from being seduced by a dramatic interpretation that later collapses under improved measurement. Even so, the existence of the debate itself reveals something important. It shows where the model is most sensitive. If dark matter is inferred from gravitational behavior, then objects that seem to deviate from the expected relationship between visible matter and gravity become high-value tests. They force everyone to ask whether the anomaly is real, whether the measurements are complete, or whether the interpretation has missed a subtle effect. It also highlights the difference between two kinds of discomfort. There is the discomfort of an object that is rare but fits within known mechanisms, and then there is the discomfort of an object that seems to chip at a basic assumption. A galaxy that looks dark matter poor, if confirmed, would not automatically overturn the Lambda Cold Dark Matter model, because a model can accommodate exceptions through unusual formation pathways. But it would demand a plausible pathway. One such pathway involves environment. NGC1052-DF2 sits in a region where interactions with larger galaxies could matter. Tidal forces can strip material away. Gravitational encounters can pull on a galaxy's outskirts. In principle, a galaxy could lose part of its dark matter halo through tidal stripping while retaining enough stars to remain visible. Another scenario involves the complex physics of galaxy formation itself, where feedback from star formation and interactions with surrounding gas can alter the distribution of matter. In these discussions, the anomaly becomes less like a contradiction and more like a clue about how galaxies are sculpted by their surroundings. There is also the alternative gravitational framework that tends to appear whenever dark matter is discussed. Modified Newtonian dynamics, often called MOND, proposed by Mordechai Milgram, attempts to explain galaxy rotation behavior by adjusting how gravity behaves at very low accelerations. MOND can fit certain galaxy rotation curves surprisingly well, but it faces difficulty matching the full range of cosmological evidence, including the cosmic microwave background and large-scale structure formation, in the same comprehensive way as the Lambda Cold Dark Matter model. Still, MOND exists as a reminder that inference is not the same as direct detection. Dark matter is the dominant interpretation, but the debate space remains, especially when anomalies invite it. All of this may sound like a dispute about bookkeeping, about how much invisible mass is or is not present. But under the surface, the philosophical weight is heavier. It is about how knowledge is built in astronomy. A galaxy cannot be handled. It cannot be sampled in a laboratory. Instead, it is interpreted through light and motion, through models and assumptions, through the interplay between what is observed and what must be true for the observation to make sense. A galaxy that seems to have no dark matter is not only an astrophysical puzzle. It is a reminder that the invisible parts of the universe are, by definition, known through indirect means. That is not a weakness. It is simply the nature of the subject. The universe is under no obligation to present itself in convenient forms. And then, just as the mind is holding that tension, the universe offers a second kind of structural discomfort. Not a galaxy missing something, but a region of space that seems to be missing almost everything. cosmic voids. On the larger scales, the universe is not a uniform fog of galaxies. It is a web. Galaxies trace out filaments and walls, clustering where dark matter and ordinary matter have gathered over billions of years. Between those dense regions lie enormous volumes where there are comparatively few galaxies. These are voids, and they can be truly immense, stretching across tens or even hundreds of millions of light-years. Voids are expected in the Lambda Cold Dark Matter model. They emerge naturally from gravitational growth. Dense regions get denser as they attract matter. Underdense regions lose matter as it flows away toward the growing clusters and filaments. Over time, the contrast increases, and the cosmic web becomes more pronounced. In that sense, voids are not anomalies. They are part of the standard story. The discomfort appears when the voids seem too large, too empty, or too sharply defined compared with what is statistically expected in simulations. When astronomers map large-scale structure using surveys like the Sloan Digital Sky Survey, they do not only see clusters and filaments. They also see the architecture of emptiness. In some cases, the emptiness feels almost aggressive, as though the universe has carved out space on a scale that makes human intuition feel small. Voids are difficult to appreciate because absence is harder to visualize than presence. A galaxy cluster is a bright congregation of light. A void is a vast region where light is sparse. But their physical reality is clear in the maps. They influence how galaxies move. They affect the flow of matter. They shape the gravitational landscape just as surely as the dense regions do, though in the opposite direction. A deep void also invites a quiet question about perspective. From inside a void, the universe could look subtly different. The local expansion rate inferred from nearby measurements could be biased. The distribution of matter could influence gravitational lensing statistics. Even the cosmic microwave background anisotropies could be interpreted through the lens of local structure. These are subtle effects, not dramatic reversals, but they illustrate how large-scale structure and local inference can interact. Voids also reveal something about scale that can feel almost unsettling. Human experience is built around objects: planets, mountains, oceans, cities. Even when thinking about space, attention often goes to stars, galaxies, and black holes. Voids demand attention to the spaces between. They insist that the universe is not only made of things, but also made of structured nothingness, patterned emptiness, shaped absence. In a sense, cosmic voids are the mirror image of galaxies that seem to lack dark matter. Both cases involve missing mass, but at different levels. A dark matter-poor galaxy would be a localized deficit of expected gravitational scaffolding. A cosmic void is a vast deficit of ordinary matter and galaxies relative to surrounding regions. Both challenge comfort not because they are impossible, but because they make the universe feel less evenly behaved than the mind wants it to be. There is also a gentle lesson in both. Models like Lambda Cold Dark Matter are statistical descriptions of a universe with tremendous variety. They describe what is typical and what is rare, but they do not guarantee that every region, every galaxy, every measurement will look neat. A cosmos built through gravity and time will naturally produce extremes. Some galaxies will be weird. Some regions will be unusually empty. Some measurements will resist clean interpretation. And that is where the philosophical weight sharpens. The goal is not to force the universe to match a tidy expectation. The goal is to build expectations that are honest enough to include what the universe actually does, even when it feels uncomfortable. A galaxy that seems to have little dark matter forces a recheck of assumptions, a search for formation pathways, and a sharper look at how mass is inferred from motion. A cosmic void forces a confrontation with scale and statistical variation, reminding anyone listening that the universe can express its laws through patterns that include enormous emptiness as well as dense congregation. Together, they pull attention back to the largest question beneath all of this. The universe is understood not only through objects, but through structure, through the way matter arranges itself and the way absence arranges itself too. It is not always a comfortable arrangement, but it is, unmistakably, the arrangement that exists. When strange objects appear in the sky, it is tempting to imagine they are shouting something dramatic, that they are announcing a flaw in physics, or a crack in the foundations, or a secret the universe can no longer keep hidden. In reality, astronomy tends to be quieter than that. The universe does not usually overturn its own rules. It tests them. It leans on their edges. It produces outliers and waits to see whether the observers can tell the difference between a genuine surprise and a misunderstanding. This is where the uncomfortable honesty of science becomes its strength. Most anomalies do not demand a new universe. They demand better measurement, better modeling, and a more careful sense of what a model is supposed to do in the first place. A model is not the universe. It is a simplified representation of it. Even the best models are selective. They choose which details matter and which details can be averaged away. And in astronomy, where the systems are vast and complex, that selectivity is not optional. It is survival. Cosmological simulations are one of the most powerful tools modern astrophysics has. They take initial conditions inspired by measurements, such as the properties of the cosmic microwave background, and then let gravity and cosmic expansion shape matter over billions of years. Simulations like the Millennium Simulation and the Illustris project have produced results that match large-scale observations with striking success, from the filamentary cosmic web to the overall distribution of galaxy clusters. But there is a crucial constraint. A simulation has a finite resolution. It cannot track everything. Galaxies, in reality, are built from processes spanning enormous ranges of scale. Gravity operates on millions of light years, but star formation occurs in cold, dense pockets of gas on much smaller scales. Supernova explosions inject energy into surrounding gas, heating it, stirring it, and sometimes driving it out of the galaxy entirely. Stellar winds, radiation pressure, magnetic fields, and turbulence all play roles. These processes are often referred to as baryonic physics because they involve ordinary matter, the protons and neutrons in gas and stars. Even the most advanced cosmological simulations cannot model every star-forming cloud directly. Instead, they use subgrid models, simplified prescriptions that approximate what happens below the resolution limit. Those prescriptions can be grounded in smaller-scale simulations and observations, but they remain approximations. They can carry uncertainties. They can shift results in subtle but important ways, especially for unusual objects. This matters because many of the strange objects discussed so far sit exactly in the regions where these uncertain processes matter most. Ultra-diffuse galaxies may be sensitive to how feedback redistributes gas and stars. The abundance of faint galaxies depends on how star formation turns on and shuts off in small halos. The distribution of matter in and around galaxies depends on gas dynamics that are hard to model cleanly. When simulations struggle to reproduce a certain class of objects, it does not automatically mean the underlying cosmology is wrong. It may mean the baryonic recipes need refinement, or it may mean the initial assumptions about environment or formation pathways were incomplete. Even in stellar physics, where models are more direct, uncertainties remain. The maximum mass of a star depends on how radiation pressure interacts within falling gas, how winds remove mass, and how metallicity influences that loss. The behavior of neutron star matter depends on an equation of state that is constrained by observations, but not fully pinned down. Magnetars live in a regime where magnetic fields become so intense that they influence the structure of matter itself, a regime far outside everyday experience. The point is not that science is vague. The point is that science is precise about where it is precise and honest about where it is not. The temptation with anomalies is to treat them like contradictions, but in practice they are often invitations to separate three possibilities. The first is that the anomaly is an error, a mismeasurement, an artifact, or a misunderstanding. The second is that the anomaly is real but explainable within existing theory once the details are understood. The third is that the anomaly is real and requires a revision of the theory itself. Astronomy has experienced all three outcomes in different contexts. There have been apparent discoveries that later vanished under better data. There have been strange observations that became normal once a mechanism was found. And there have been moments when the theory truly had to change. To navigate these possibilities, scientists rely heavily on statistics. That word can feel dry, but it is one of the essential tools for keeping interpretation honest. The universe produces variation. Even if the Lambda Cold Dark Matter model is correct, it does not predict a single galaxy. It predicts a distribution of galaxies. It predicts probabilities. It predicts what is common and what is rare. An anomaly, therefore, is often not a thing that should never happen. It is a thing that should happen so rarely that seeing it makes people pause and count again. This is where ideas like confidence and significance come in. In many areas of physics, a high threshold is used for claiming a discovery. Particle physics at CERN often talks about the 5 sigma standard, meaning an extremely low probability that the signal is a random fluctuation. Astronomy uses similar statistical caution, though the exact details depend on the context. The core idea is the same. Rare events occur by chance. If a dataset is large enough, even very low probability outcomes can appear somewhere. That is not magic. That is mathematics. Consider a simple example in spirit, even if the universe itself is not simple. If a particular kind of object is expected to occur once in a million cases, and the universe contains many more than a million relevant cases, then the appearance of such an object is not a contradiction. It is the expected consequence of having a huge sample size. The cosmos is so large that its tail events are not merely theoretical. They become visible. This statistical perspective also warns against a common trap. Humans are pattern seekers. A single striking object can feel like a revelation. But science asks whether it is part of a population, whether it repeats, whether it is consistent across different observations and different instruments. That is why debates about objects like NGC 1052-D F2 focus so much on measurement. If a claim would have major consequences, the measurement must survive intense scrutiny. Distance estimates must be checked. Velocity dispersions must be confirmed. Systematic biases must be ruled out. The same discipline applies to fast radio bursts. A single burst could be interference. A population of bursts with consistent dispersion measures and localization to host galaxies becomes harder to dismiss. Repeating sources strengthen the case that an astrophysical engine is at work. Localization efforts using multiple telescopes turn fleeting signals into measurable phenomena that can be connected to environments and mechanisms. This is also why simulations and observations are in constant conversation. Observations suggest what exists. Simulations test whether those objects fit within known physics. When the two disagree, it does not mean one side is broken. It means the gap between them is where learning happens. Sometimes the gap closes because the model improves. Sometimes it closes because the measurements improve. Sometimes it stays open long enough to indicate that a deeper revision is needed. A useful way to think about it is that science is not a list of answers. It is a method for managing uncertainty while steadily shrinking it. That brings the narrative to a calmer and more human place. The objects that seem as though they should not exist often feel that way because they sit at the boundary between what is well modeled and what is still emerging. They are uncomfortable because they expose the limits of prediction, not the failure of physics. They remind anyone listening that the universe is not obliged to generate only the most typical outcomes. It will generate extremes, and it will do so without explanation, because explanation is something observers supply after the fact. There is also a deeper philosophical resolution hidden in this. The phrase "should not exist" is not a statement about the universe. It is a statement about expectation. It reveals how human beings think. A model becomes familiar. Its typical predictions become comfortable. It begins to feel like a law of nature rather than a best current description. Then an object appears that forces a pause, and suddenly it becomes obvious again that the model is a map, not the territory. This does not reduce the value of the map. A good map is astonishing. It can guide, predict, and reveal. The Lambda Cold Dark Matter model, General Relativity, stellar evolution theory, and the physics of nuclear fusion have explained vast portions of reality with extraordinary success. The cosmic microwave background matches predictions of early universe cosmology. Gravitational lensing matches general relativity. Neutron star observations constrain matter physics in ways no laboratory can. These are not weak achievements. They are some of the strongest achievements in human knowledge. But a map is still an abstraction, and the universe is still richer than abstraction. That is why anomalies are not enemies of science. They are part of science's natural ecosystem. They keep models honest. They prevent comfort from turning into complacency. They point to where details matter. They remind everyone that nature is allowed to be more varied than prediction assumes. There is a gentle kind of wonder in that, especially at night. The sky can feel steady and timeless, but it is full of edge cases, ghostly galaxies, stars flung into darkness, magnetic remnants with fields that challenge intuition, bursts of radio light that last only milliseconds, black holes that may have formed before the first stars, voids so vast they make emptiness feel structured. Each one is a real object or real phenomenon, and each one carries a message of a particular kind. Not a message that physics is wrong, but a message that physics, applied to a universe of this size, will sometimes produce outcomes that look unusual simply because the universe has enough room to explore every possibility permitted by its laws. And that is the calm resolution. The universe is lawful, but it is not obligated to be typical. It can produce the expected outcomes most of the time and still produce rare outliers, because it has had billions of years and unimaginable volume to do so. The strange objects do not demand that reality be rewritten. They demand that expectations be kept flexible. In that sense, the objects that should not exist are not mistakes. They are the universe showing its full range.